All right, so the last module will answer exactly the question I asked in the second module. So when you have that J theta loss function like write out clearly, how do you minimize it? And we're going to cover the specific solution called normal equation based solution. All right, so to get it started first, so there's some kind of notation, again, concise notation, and we actually showed you, so there are different ways to represent your training samples. And for example, this is my training sample X1, and it's a vector. And then its column form is this P times 1, P plus 1 times 1, because the first one, again, is this pseudo, it's a pseudo feature, just to easier to learn, to easier to write everything as a vector or matrix form, to learn the intercept Bayes term. And so it's the column form, and this transition is the row form. And then we can write our training data as this n times p matrix. So I will not talk more because I already covered. So again, so this is the feature dimension, and this is the sample, different samples. So again, it will be very clear why I'm keep emphasizing n times p in just a few slides. All right, so we actually can represent that x times theta operation, not just using like what we did in our simple sample. So you write out every one of those. You actually don't need to do that. The whole operation applying this f into every sample in my training data can be just summarized into this much more concise notation. It's just this x times theta. X is my matrix, size n times p, and theta, I can do p plus 1, but just, yeah, p, let's just assume all the features. I think I wrote as p plus 1. Yeah, I should write as p plus 1, but that's, yeah, just assuming this p, it's always including one of the pseudo features, just make the future easier, because it's always just a scalar in that notation. So it's n times p, and then my, yeah, again, but I still write as p times 1 just to not get you confused. And my theta vector is a p plus 1 times 1 vector. And then this totally matched in terms of matrix vector multiplication. And this is exactly equivalent to you are doing that x1 transposition theta onto xn transposition theta. So this is a much more concise way to write it. All right, and then you can just do rederive this summation based notation into a matrix multiplication, and then this is how you derive it. I'm not going to do that. And then you can convert your J theta into this totally matrix vector concise form. And then you can actually tell this if this is an equation. So let's look at, so J theta and theta. So this is in fact a quadratic function on that variable to be looked for on the theta. So this is J theta is my function to minimize, and then it is a function, it is a quadratic function of my variable. In this case, variable is theta vector. So if you do not understand it, that's okay. So we're going to do an extremely simpler case, simplified case. So what do I mean quadratic function? So let's assume we have only one parameter to look for, like W, and this is a quadratic function. So this is W, this is LW. And we actually know how to minimize a quadratic function. So let's see this extremely simple case, right? How do you minimize this simple, really simple one-dimensional quadratic function? The minimal, because it's quadratic, right? It's this kind of valley shape, and there's only one minimal point that point, the derivative is equals to 0. So we can just take derivative for this LW function, and its derivative is, so hopefully you still remember what's the quadratic function's derivative, which is 2w. Then the scalar has no derivative because it's a known, it's not relevant to w. And then the derivative of that quadratic function is 2w. And the minimal point of LW is the point that makes the derivative equal to 0. And this just tells me, oh, I should actually write out argmin L prime 0 is the one, actually no, yeah, I should. It's not very complete. Okay, so there's some error here. So argmin W equals to the solution that makes L prime W equals to 0. And this gives me the best W star. Yeah, so the solution from making the derivative equals 0 is the point that minimize my LW. So there are many different kinds of loss functions. I mean, so let's just, so it can be like go up, this is called convex. It can go down, this is called concave. It also can do this, the third shape. So for the convex and concave functions, so for so this is like convex shape, right? So convex function has this minimal point, and it's the point that gives you the gradient. 0 point is the point give you the minimal of this convex function. The concave function, there's no minimal, but there's maximal. And there's other cases like it's really going to positive infinity and going to negative infinity. And it also has those points that gradient is 0, but this point, it's not minimal, it's also not maximal. And this is normally called saddle point. So we're going to talk about this in the future slide, but for now, in the linear regression case, so linear regression is such a great J function. So the reason why we pick J theta as that form, summation 1 from I from 1 to, sorry, 1 from n, the linear form, which is the xi transposition theta minus, oh God, I'm so sorry. Somehow it's cut. Minus yi, take quadratic, and this sum of square area is a good convex function. And there's a reason why we picked this instead of picking some other type of loss function, right? We can do absolute differences, but absolute differences is much harder to do differentiation. And the square function, it's much easier to take derivative or partial derivative operations. That's part of the reason why we, in the linear regression case, and this is the most popular and always is the first one we normally learn. All right, so so J theta, and then we have J theta form, and then the best theta is the one. We found the best theta just by solving its partial derivative to make it 0, actually, because now theta is a vector. It's not just one scalar anymore. It's when you take partial derivative, this is actually called a gradient. It's a gradient vector. So the way to minimize J theta is just to get this gradient vector, and then you set it to 0. And this gives us the solution and give this formulation. And I have a totally detailed how to derive it. If you're interested, go to see the extra page. And then you can directly got the best solution. Theta star has this form, which is x transposition x, then together take an inverse, and then times x transposition, then y. So everything here is about is the train part. X train, y train, yeah. So this is what we normally see. It's a normal equation-based closed form solution. And we're going to talk about what do we mean closed form solution in the next, next class. All right, so this is about how to derive it. I'm not going to cover that, but feel free to check it out. Yeah. And it's pretty doable if you're familiar with this type of matrix multiplication or matrix vector multiplications. So I want to do this concrete. Should I do it? Okay, so let me do a concrete, just make it complete, right? So there are 4 minutes. I think I should be able to finish that, but now because I have only 4 minutes, I will only have 2 samples, have 2 samples, xi, yi. So let's remember what is our JWB looks like. If you still remember, that is W plus B minus 2 quadratic plus 2W plus B minus 3 quadratic. So I will not put a third point, just make it a little bit harder. So I will have only 2 points. Okay, so now I'm going to take partial derivatives of this loss function. And what should I get from here? So it's actually pretty simple. It just, when you take derivative versus W, this give me 2. I think it just 2W plus B minus 2, right? Just help me check. Plus 2. Oh, I have the 1/2 here, right? So the 2 has this 1/2, which actually cancel out with that 1/2, which that's the reason why there's a 1/2 in the JC the formulation. So I have this 2W plus B minus 3, then times 2. I think this is correct. And then I set it to 0. And then I do the same thing for B. This equals to, again, 2 W plus B minus 2 plus like just 2W plus B minus 3. This is correct, right? I think so. Okay, now you have what to solve. You have a linear equation, just 2 linear, it's just a linear equation to solve. So what do I get? I don't remember what I had before, but I think I have to solve it in some. Let me check that just to make it quick. Yeah. Okay, I have to solve it. Yeah, I will solve it. All right, so what do we get from this? I think we get 5W plus 3B minus 8. Is this correct for the first one? Please correct me if I'm wrong. And then we have 3W plus 2B minus 5 equal to 0. Is this correct? Seem to be correct. So who can help me solve this? Oh, I have to cancel out let me see which one to cancel out. So let me make it derivative. Hopefully you still remember how to do this. I will try to cancel out the 3B by times 3 and times 2. So this is 10W plus 6B minus 16 equal to 0. And then this is 9W plus 6B it's times 15. Yes, I think I'm correct. Yeah, okay, so what is W here? It's super easy. I get W equals to 1. I think after I get W equals to 1, I will get B equals to 1, 2, right? Because B equals to 1 over 2, 3. Oh, no, 3W. 5 minus 3W. 3W, which is, sorry, which is 1. Okay, so voila, we solved it 1, 1. Okay, so eyeball, it's so easy, right? But actually, what truly your eyeball is truly does this. And then using this math notation, you got the J theta, JWE function, and then you set its partial derivative for each one of the theta. In this case, there are 2 parameters, W and B. You set them as 0, you got a equation array. There are 2 linear equations with 2 variables, and then you can solve it 1, 1. All right, so I think this is all I want to say about the, yeah, so everything else is I try to do this concrete derivation, which I found is very good because you truly got that. So the one thing I use, I hope you still remember, what is that? This is called Gaussian elimination base to solve the matrix equations. And this is the end of module 3. And we're going to cover the module 4 in the